Right, so last time we were talking about convex optimization. We looked at some of the fundamentals, right? The notion of convex sets, convex functions. And then we're starting to look at some well-known form of convex optimization problems and some applications in wireless communications, right? And one of the examples that we started with was, and actually this is the example one among the many that we're going to have in this part of on convex optimization, it was this transmitter beamforming with power minimization, right? So this was the case where you have a transmitter and you have multiple receivers. So we have a downlink scenario, and we transmit unicast information, right? So those are independent streams that you transmit to each of those users. So I have one beam for user 1, one beam for user 2, one beam for user 3, carrying different information. And what you want to do is that you want to guarantee that you have a certain quality of service there, and there. So you have a certain, signals to interference plus noise ratio. Why is this not moving? Right. So this is our signals to interference plus noise ratio that we have to guarantee. And you see, when you look at a given user I, this user I see interference from the other users, right? So when I'm looking at the SINR of user 1 here, when I want to essentially decode the streams of user 1, I'm subject to interference from the other beams here that carries information for user 2 and user 3, right? And I want to minimize the total power consumptions, right, to guarantee a certain quality of service, right? So this is a different problem from sum rate maximization. In sum rate maximization, we'll come back to this later on. In sum rate maximization, you want to maximize the sum rate. So the sum rate is a function of the SINR, but you subject to a constraint that is the power constraints. So it's a little bit the opposite problem, if you like, right? So we'll come back to this later on, because this one is actually easier to handle. Right, and I mentioned last time we have three solutions to solve that problem. And what we looked at is this second-order cone program, so this SOCP. And today we'll continue with the SDP and the KKT. And we'll look at other examples as well. Right, so what we ended up with is this transformation where we have our minimization of the transmit power subject to quality of service or SINR constraints end up being essentially reformulated as a SOCP, where I have here two cone constraints, and here I have a linear functions to minimize, right? And so we finished with this 2 weeks ago, 3 weeks ago. And what I want to show you is how you can now implement this into a software that is called CVX that is used to solve convex optimization problem. So this was developed by this team here. Stephen Boyd is a professor at Stanford. He's very well known in the area of convex optimization. And so they came up with this software. There are many different softwares to solve convex optimization problems, but this one is very popular because it's open source and essentially is used extensively in the academic literature. So what you're going to have to do in coursework 3, you're going to have a problem related to wireless communication. You're going to have to optimize it, and you're going to have to use MATLAB together with CVX to solve this problem. So throughout the lectures today, you will see several examples on how you can use this CVX tool to actually solve, examples of communication, optimization of communication systems. So this is the example here that I wrote for this SOCP. When we have transmit beamformer and we want to minimize the power. So I have, this comes essentially within your MATLAB program. Within the MATLAB code, you're going to generate your channel realization, for instance, right, with a certain model, blah, blah, blah. And at some point, you will say, okay, now I have my beamformer. I want to optimize them, right? And so you will enter essentially CVX. You will call CVX. And this is done by doing CVX begin and CVX end. And within those two lines, essentially, you write your optimization problem as it is here. Okay? So here's an example. I want to minimize tau subject to those two constraints. So how you can do that, and you will play with this quite a bit, you know, in the classes with Yang and Hongyu. But here I actually declare two variables, tau, that is non-negative, that I want to essentially minimize here, which is my objective function here. And I have my variable W, which is complex, which is here this matrix, which is the one I want to find, essentially, right? And so I'm saying I minimize tau subject to, and I'm writing my constraint here. And so I have k constraints here. Those k constraints comes from the k constraints I have from this ones here. So I have for all i's going from 1 to k, so I have k constraints, k cone constraints here, plus an additional cone constraint there, right? So I'm writing those k plus 1 constraint in my CVX code here. I have the k first one, and then I have the second one. So this is saying I have the norm of the vector of W that is smaller than the square root of tau. This is exactly the same as what we have in the mathematical formulation. And then I have this one that is a little bit more tricky. The first one that says I have a norm of a matrix here, right? So this part here is actually the same as this part here. This is the norm of that matrix. And then it has to be smaller than something, right? Now here you remember what we said. For this to be a valid constraint, a cone constraint, this one has to be essentially a real quantity, a scalar that is real. And so what we were doing, we can always find your W here such that this quantity is real, right? Because you remember what I explained. You can always say, I take a W, and if I multiply my W by just a phasor, right? I don't change anything to the directions of this precoder, right? So the solution will still be valid, but by doing this, actually I can render this, make this quantity real, right? That's what we were talking about last time. So here I'm doing the same, and I'm saying, okay, now if this is real, I can write this is actually a real quantity, right? And so that's why in the code I'm saying this is smaller than a certain quantity, real multiplied by real of that part. And I'm enforcing the second part, the imaginary part, to be equal to 0. So I'm essentially reflecting in the CVX code exactly what we were saying 2 weeks ago, where we had effectively this W, we could choose the phase that this comes real. And so by being real, actually the imaginary part of this quantity is equal to 0. And I expressively write this down into the CVX code here. Right? So you will see, you will learn a little bit when you do those exercises, you will learn how to write CVX programs properly. And you will see, I will give you some examples. And sometimes you have to tweak a little bit because CVX expects you to write your convex program in a certain form. And if you don't write it in a certain form, essentially it will come up with an error because it's not written exactly in the form that is required. Right, so if you do that, you can run this, and what this will give you, it will give you this minimum value here of this tau, and it will give you the value of omega, of W, that minimize this function. Right. So this was, and I will show you some simulation results in a minute. So this was about this SOCP. There is another way, and very popular way, maybe a slightly more general way, to formulate an optimization problem is using this semi-definite programming, so called SDP. So we saw the linear program, we saw the quadratic program and quadratic constraint, quadratic program with quadratic constraints. We saw this second order cone program, and now this is the semi-definite program. And this one is actually a form of actually an optimization problem that is slightly more general than the three other ones. Right, so what do we have here is a set of optimization problem where we have linear objective function that is represented by this. We have linear equality constraint, which is represented by this one. And then we have a constraint on the matrix X that says that this matrix has to be semi-definite positive, right? So this is linear, right? Because this is actually matrix multiplication. This is a trace, so essentially this will be a linear function of the entries of X, right? And similarly here, this is linear. And this problem, so this is a linear function, but this is convex objective function, right? This is a linear constraint, so this will be actually a convex constraint as well. And X here is semi-definite, and remember, this is actually among all the set of semi-definite matrices, it forms a convex cone, remember? And if this is a bit, just to refresh a bit, we had this here. So if you look at, you take you take two matrices A and B that are semi-definite positive, and you take a linear combination of those two, this linear combination will still be semi-definite positive, right? So this was actually the proof of why this set of positive semi-definite matrices is a convex one. So what we end up with is a linear objective function, a linear constraint, and then a convex set that is obtained from this convex cone, right? So we have actually now a convex optimization problem, right? Okay, so I'm giving you here a very useful property, and this may look a little bit cumbersome, but you will see we'll use this very quickly in the next slide. It says the following. If you have a matrix that you can write into blocks where you have some symmetry here, you have B and B transpose, and you have A and C, well, this matrix will be semi-definite positive if this block is semi-definite positive, and if you have this transformation, this quantity, that is obtained by taking C minus the product of BT AB, and you take the inverse of A, if this quantity is positive as well. So this is semi-definite positive if A is semi-definite positive and this one is semi-definite positive, and you have the opposite relationship as well. If you have this and this as semi-definite positive, you can conclude that this matrix is semi-definite positive, right? So let's look at this on a specific example, which is this one, right? So what can you do here? You say, well, this is semi-definite positive if and only if, well, A has to be semi-definite positive, so that means actually this quantity has to be semi-definite positive. What does that mean is essentially this quantity here, this is an identity matrix, so this one has to be positive. That's what it says. And this is what we have here. And the second constraint here says you do C minus this quantity. What is that this? C is this one, right? So if I write this down, I have CT X plus D, right? Minus BT, so I have AX plus B transpose. A minus 1, so I have the inverse of this quantity multiplied by B here, multiplied by B, and B is this part here. So I have AX plus B. Right? Okay, so the inverse of this is an identity matrix. This is nothing else than 1 over CT X plus D. This is a scalar, right? And this has to be positive, but this is a scalar and this is a scalar, so it ends up just being positive. That's what it means. Right? So here I have a vector multiplied by a vector. So this will be nothing else than CT X plus D. And I can bring this to the other side. So this is complex. This is real in this example. So this is C is real and X is real. So the square of those two will be, the multiplication of those two will be the magnitude square. And then I have here the product of those two. So I have essentially a vector and a vector, the inner product. So I end up with the norm square of this vector. Okay, so I have the same as there. Plus the first condition that this term is positive, right? That coming from A is equal to is positive. So I have this is my second condition. This is my first condition. CTX plus D is positive. And so from those two here, this is positive. This term is this term is positive. And so I can cancel. I can write this equivalently as saying CTX plus D has to be larger than AX plus B. And I can do this. I can remove the square here because we know that this quantity is positive from here. Right? Right. So what I did here is simply say, essentially, I have a matrix X that can be written as this. If it's written by this, by this form here, I say this one will be semi-definite positive, and I can write this condition on semi-definite positiveness. Equivalent can be written as this, saying I have a second L2 norm here of this vector will be smaller than a scalar, right? So this is reminiscent of a second order cone program. This is a second order cone. So why I want to show you this is because I want to show you that if you start from an X that has this structure, you can actually convert this into a structure that like this, just to show you that actually there is an equivalence between a second order cone program and a semi-definite program. Right. Why is it still not working here? Right. So let me show you first how a linear program is a particular form of a semi-definite program. So a linear program, you remember, says I have a linear objective function and I have linear inequalities here, right? Essentially, you remember this. This is a vector. This is a matrix. So this is a vector, and I say that each entry of that vector must be smaller than the entries of B, essentially, right? So I have a set of linear inequalities, essentially, and I can write this equivalently as something like this. That say, well, instead of having a set of linear inequalities, I can form a matrix, a diagonal matrix here, by saying I bring B on the other side. And now I have a vector here, and I create a matrix from this vector that is now a diagonal of this. So those are essentially the entries of that vector becomes the entries of that diagonal matrix. And so I've now created a matrix, and I'm saying that matrix has to be semi-definite negative. Or you can have written this differently and saying I have the diag of B minus AX has to be semi-definite positive, right? And so this is essentially a matrix that has to be semi-definite positive, and I have a linear constraint, so this is actually a semi-definite program, right? So that shows you how this linear program can be written in a SDP form, essentially. And so what you can show is that, I will not do this, but you can show that LP is a subset of QCQP. I've shown you this already before. QCQP is a subset of OCP. I mentioned this before. And you see here this example, LP is a subset of SDP. And I will show you in a minute that SOCP is a subset of SDP, right? So that means that you can, if you don't know exactly what problem it is, you can try to always formulate it into an SDP. But this has a cost as well, because when you want to solve it, solving an SDP is actually more complicated than solving an OCP, solving QCQP, and solving an LP, right? So the efficiency of the solution is higher if you can show that the program is linear, it's a linear program, then all the current, optimization techniques to solve convex optimization problem, which will not go into this module, essentially they're more efficient if the problem is simpler. Simpler means, for instance, you have a linear program, right? So for SDP, it would be a bit more complicated than for the other problems. But nevertheless, the technology has evolved, and nowadays SDP can run this very, very efficiently. And so, for instance, in CVX, as far as I know, everything is solved using these SDP formulations. Right? If you have this kind of formulation, I think the solver is essentially an SDP solver. I think that's the way it's implemented. Right. But nevertheless, it's important for you to realize, try to really understand when is a problem really LP, QC, QP, SOCP, SDP, because it's very important to try to recognize the form of convex optimization problems that you have. Okay, so let me show you now how this SOCP is a subset of SDP. So I want to show you this part here, that SOCP is essentially a particular form of SDP. So in SOCP, remember we had a linear objective function, and we had this cone constraint, right? And I was telling you here on the board that, well, you see this constraint here essentially is the same as having this with this, which those two comes from the fact that we have this semi-definite positive constraint, right? So we had this matrix before, and we were saying, when is this semi-definite positive? When you can say that this term is positive, so that was our first constraint, and you say that this matrix S was positive, which was this one minus this one, A inverse here multiplied by this one, which is this one, and when you take those two constraints here, essentially you can show that those two constraints are the same as this, so those two constraints becomes this. Right? So writing in this way, or writing in this way, you actually, the difference between the two is that when you write it this way, this is really written formally as a second-order cone program. When you write it this way, you write it as a semi-definite program. And so what I show you here is that you have equivalence between those two formulations. And so this one can indeed be written as this form, where this now, the constraint is on having this to be semi-definite positive. Right? So if you have a problem like this, you can always solve using SOCP solver, or you can solve it using an SDP solver. Right? Right. Okay, so let's go back to our example. And our example 1 was this power minimization when we had this transmit beamforming. So I still have the same problem as here. I want to minimize the power here subject to SINR constraint. So my objective function is the norm square of each of those precoding vectors, right? So this quantity, the norm square, this will be the power I allocate to user I, or to user J here, right? So I have every time a precoder, remember this, I have a precoder, and essentially the norm of that precoder will tell me how much power I allocate to user 3, how much power I allocate to user 2, how much power I allocate to user 1. And so the sum over those k will tell me the total power that I allocate to, that I transmit over the year, essentially. So this is my transmit power. And I can formulate this differently using a trace here. You know this transformation already. So I'm just writing this differently, nothing very complicated here. What is more interesting is this transformation here. I have this SINR constraint, and now I'm saying, well, I can write my numerator equivalently like this. So I have this is essentially a scalar, right? So just do it once again, just to make sure that you follow this. So I have this HI, it's always the same kind of trick, right? This quantity, this is the same as saying this is HI emission, WI HI emission conjugate, essentially, right? Sorry. HI emission, WI conjugate. So this is the same as HI WI emission HI. Right? Or I could even say this. It doesn't change anything. So I have this like this. See? Right? So I have here my WI emission. Right? And this is my term here. And this is a scalar. This is a scalar. So I can say this is the same as a trace. I don't add anything here. I just add the trace, but this is a scalar, so the trace of a scalar is still a scalar. Right? And I'm doing that. Okay? And now the next step after will be, well, if you have this kind of stuff, you can always say, you can move your vectors here. This is again properties of those trace. And now I have a matrix, a function of H, and a matrix function of W. Okay? So this is what I'm doing here. I have now a trace of this quantity, and I do the same now for the denominator. Right? And you remember what we were saying before? This kind of constraint typically is non-convex, because this is like a quadratic form minus another quadratic form. Right? And this is typically non-convex, right? And so this is, if you remember, the same problem as before, where we're saying this here, right? We have this. Now what I have done, I have just shuffled the terms, right? I have brought those one on the exterior, so I have written this differently. And the reason why I write it differently is because I want to express this differently as well, using SDP form. Right? So here you see really the quadratic form. You have a matrix and you have the W on each side. And then you have a difference of quadratic form. This is typically non-convex, but we solve this using SOCP. Nevertheless, it's quite a unique form that can be solved optimally. Now I'm changing this because I want to explore the SDP formulation. Right? So let's go back to this. And now I have these SDP formulations that will appear progressively. Because what do I need for an SDP formulation? I need to have linear constraints, a linear objective function, and I need to have a constraints on a semi-definite matrix, semi-definite positive matrix, right? So I have to minimize this quantity subject to these constraints. So where can I find now an SDP here? Well, the trick is to say, I will write this as a matrix. I will not say it's a multiplication of two vectors. I will say this is a matrix X. And I will say this matrix X or Xi. And then here I'm going to have Xi and Xj. And those matrices, they have to be semi-definite positive. So let me write this differently. Xi or Xj or Bj, right? So I'm saying now I have this quantity. Where I replace this, this becomes the sum of trace of a matrix. Right? But I have lost some information by saying this, because this matrix is a matrix indeed, but it's a rank 1 matrix. It's a vector multiplied by this Hermitian. So this is clearly rank 1. So if I replace it and say this is just a matrix, this is not really sufficient. Right? But nevertheless, let's do that for the time being. And this is actually Hermitian matrix. This is actually semi-definite positive. Right? So let's write this. I have a matrix B. Right? That's my objective function. And then here my trace, I have H here, that I will write H. And then I have again this matrix that will be my BI. And here I will have some BJ. Okay, so I'm just replacing this by matrices. Okay? And I'm saying those matrices are semi-definite positive. So this is nice, because now I have an SDP problem that says, well, if instead of looking for the W, instead of looking for those precoders, right, you look for matrices, well, this formulation here can be written as something like this, that is an SDP formulation. This is linear in the entries of B, this is linear in the entries of B, and this is actually a semi-definite constraint. But you have to keep in mind that, well, those h, this is not a problem, those h as a product of those vectors, that's okay. But here, those b, they're actually the product of those two vectors, right? So if you just write it like this is not equivalent to the previous problem because you know you have not captured the fact that b must be rank 1. If you say b is rank 1, then you know that actually you can find your w afterwards because your w will be actually a rank 1 formulation of your b. But if you just say this without saying that it's rank 1, then it's not exactly the same as before. You have essentially relaxed the problem. We speak about relaxation in the sense that this problem is the same as before when you have not considered the rank constraint on those B matrices. Okay? So here we have an SDP formulation where we have relaxed the constraint on the rank of B. And so this is sometimes called SDP relaxation or semi-definite relaxation, right? What is interesting with that specific problem is that even though you remove the rank constraints, you can show that this problem has actually a rank 1 solution, right? So you solved using CVX this problem. You obtain some matrix B, which are now your objective, your optimization variables. And the solution of this will be rank 1, even though you have not asked it to be rank 1. Right? And because it's rank 1, it's nice because our original problem was actually using vectors, so using matrices B that is rank 1. Right? So we have relaxed the problem, but nevertheless, the solution of the relaxed problem still satisfied this rank 1 constraint that was needed in the original problem. Okay, so you will see this quite a bit, in communications, if you do PhD or further research, or in signal processing as well, this notion of semi-definite relaxation. But it was shown in those papers, in this one, that interestingly, this problem, even though we do not write rank 1 constraint, this still has a rank 1 solution. Right? So I will come back to SDP or semi-definite relaxation in a minute, so you will understand this a little bit better. But this is interesting. And so why, essentially, we know that there must be a rank 1 solution? Because we found out already before that this SOCP can solve the problem optimally. So there is actually a convex, a solution, a global optimal solution to that problem. And so since SDP is a more general form than SOCP, it makes sense that the SDP will also find out the global optimum solution, right? But nevertheless, it was shown actually the solution is rank 1, so it really corresponds or actually matches a little bit the observation we have with the SOCP in the sense that now we have two ways to solve the problem. You can formulate using an SOCP, or you can formulate it using SDP. And you can write your problems, whether you write it this form in CVX, or you can write it in this form in CVX, you're going to get the same solution. Right? So this tells you how you can have the same optimization problem, but you can formulate very differently, and you get a different optimization formulation, and it could have also consequences on how efficient it is to solve the problem. So let me show you some code implementation here that I wrote for this same problem. So this power minimization with transmit beamformer, but now using this SDP. Okay, so this one is a bit longer. I have my x. The x are essentially my b. Those x here are the variables. Those are the b's. Right? So those are the objective variables. And what we want to find, we want to find those x. So I also have a variable s, And I will show you in a minute why I have a variable s. I have an objective function here. This is my sum of the trace, right, of the b's. So this is the sum of the trace of the b's here. And now I'm writing here, I'm writing a constraint on this quantity. This stuff here is, this line is essentially the same as this line. Not exactly. I have a trace minus a sum of the trace that has to be larger than something. Okay? I have a trace minus a sum of a trace that comes from this line minus something has to be equal to something. So I had an inequality before, and here I have an equality. Okay? So why do I have that? Is because CVX in the SDP formulation, CVX expects an equality here. So if you write, if I have trace of AIX is equal to B, BI, right? CVX expects this, right? But in our problem formulation, we didn't have an equality there. We had an inequality. Right? So how can I transform an inequality into an equality? I can say, let's imagine I have this. This trace has to be always larger than this. What I can say, this will be essentially equivalent to saying I have trace of AIX minus another variable that is called here, this called this auxiliary slack variable, right? Equal to BI. And I'm saying S has to be positive, right? If S is positive or equal to 0, this term, the trace, will always be larger or equal to BI, right? So if I have an inequality constraint, and CVX expects me to write this as an equality constraint, essentially I can say, well, this is my equality constraint that is obtained by introducing an additional variable that is called here slack variable that is just there to replace the inequality constraints into an equality constraints, right? So this is what we have here, and this is what CVX expects for this kind of relationship. This is always fine. This is not an issue. And so that's why you have here an equality constraints, and here you have an inequality on positive. So sometimes you have to play with this, and so if you read the rules of CVX, you will find out this. Right, and then I have an additional constraint here that say X has to be semi-definite positive, because this is essentially saying that my B's are semi-definite positive, right? So now I have here a problem formulation that is CVX compliant, and so if you run this, essentially it will find those variable X and S that actually minimize this objective function. Okay? Yeah.
Wouldn't we have to use programs or programs like CVX? Is it because we can't like derive a closed formula for the minimum?
Yes. Yes. So you will see this is solved numerically, and I will explain you later on. So some optimization, convex optimization problem, you can find closed form solution. But for many of them, it's actually very, very difficult to find that. So those are solved numerically. And the main tools to solve this kind of optimization problem is called an inter-point method, which if you take course on advanced optimization, you will learn about how this works. But this is really the key that is used to actually solve those problems. But we'll not go into this module, because the key that we have is that this is designed by really, mathematicians to actually really design this interior point method in the most efficient way. What we try to do is say, okay, if you have an optimization problem, how you can formulate in a way that is convex, even though apparently it doesn't look like convex, but sometimes you can formulate differently so that you make it convex. Once it's convex, you can say you can rely on state-of-the-art tools. So this step of transformation is actually very, very complex because on those problems, they look relatively simple. Those are simple problems where people have found that actually you can convert this into convex problems. But then the problems can easily get bigger and bigger and bigger. And the key is how you can simplify this and try to relate this to a convex problem. Once you have a convex problem, with state-of-the-art tools, you know that you can find a global optimal solution using these interior point methods, for instance. But there are cases where you can find this solution analytically. And using later on what we're going to see, the Lagrangian and Karush-Kuhn-Tucker conditions. So those are necessary and sufficient conditions for global optimality when you have convex optimization problem. And for instance, the water filling solution is a very nice example where you find a closed form solution to a convex problem. But not all of them you can find this, very nicely. Yeah. Right, so let's look at some simulation results. So this is using SDP here. And my objective values here is this power minimization. I have 4 transmit antennas and 4 users. So here I have 4 users and 4 transmit antennas. My gamma is equal to 1. My noise power here is equal to 1. So those quantity here are equal to 1. So this term is equal to 1 essentially. Okay? And I generate here 100 random channel realization. What that means is that I have 4 users, 4 transmit antennas. So I generate 4 channel vectors, right? 1 for each user, and I do this 100 times, right? So one channel number 1 is essentially 4 realization of those channel state information for those 4 users, okay? And, okay, I have a first channel realization for those 4 users, and I'll get an objective value that is equal to 1. And then I randomly drop users again, so I have a different set of channel realization. I have another objective value, so objective is a function of the channels, right? All those, this quantity is a function of hi, which is itself a function of those quantities, right? So whenever you drop new users, or actually you consider new channel realization, obviously you have to run these optimization problems again, right? So this is what you see here. I do this for 100 different channel realization. And so the power, the objective, the power minimizations actually fluctuate. Sometimes I have low power, sometimes I have high power, because depending on this channel state, those age for those different users, sometimes it requires more power or less power to achieve the same constraint, the same SNR constraint for all the users, right? Which is quite intuitive. If you change the parameters, so here you go from 4 antennas to 10 antennas. Oops. I've go from 4 to 10, right? So what do you expect? You have 4 users. In the first case, you have 4 antennas. The second case, you have 10 antennas. Which one do you think would lead to a lower power at the transmitter? Sorry? 10, right. It's quite obvious, right? If you have more antennas at the transmitter, you have a better way to manage the interference, and at the same time you can benefit from this beamforming gain or the array gain, right? If you do naively, if I do here naively in this objective here, if I design my W using maximum ratio transmission, for instance, that would be maybe one solution, but maybe that solution is not good enough to satisfy this constraint, right? But if I have more antennas and I optimize those precoders, I will be able to better manage the interference between the users, right? Achieve a better beamforming gain, and so that means actually I will have a better objective functions, right? So, and I have essentially, I have more degrees of freedom, not degrees of freedom in the same way as in the MIMO case, right? But more, I have a larger optimization space. Essentially, I have each vectors now, or each matrices now is size 10 by 10, right? I still have the same number of users, but I have larger matrices to optimize. So I have more space for optimization, and that's why you see that on average you lie here around 1, 2, right? Whatever unit it is, and now you decrease, and now you're around 0.4, 0.5, something like this, right? So you see that indeed you have decreased the objective function. Right, so what if now I increase the number of users? Right, so I have 10 antenna, I have 4 users, and then I go now to 10 users with same number of antennas. What do you expect? The power should increase, right? You increase the number of users, and you have more constraints at the receiver, because instead of having 4 users that have to, for which the SINR has to be larger than a certain threshold, now you have 10 users, right? So you have more constraints. So actually that means actually it's more difficult for the transmitter to find a nice precoder that will really satisfy all those 10 constraints. And that leads to a higher transmit power in order to satisfy those 10 constraints, right? And that's why you see between here where you go at 0.4, 0.5 something, now you jump to 2 or something, right? So you have higher transmit power that is needed to satisfy all those constraints. Right. Let's go back to 4 antennas and 4 users. And now here I have 2 solutions. I have the SOCP solution, so that's using the first CVX code I showed you. And now I have this SDP or SDR, so semi-definite relaxation or semi-definite program, but in this case the 2 are the same because you don't need to do any relaxation. You're going to get a rank 1 solution. And what you see is that this is for 100 channel realization, and you obtain exactly the same solution using the 2 formulation. Whether you do SOCP or you do the SDP, SOCP is in red, and you get the same solution as in blue, the circles, right? So you get, indeed, it's originally looks like a non-convex optimization problem, but actually, because of the uniqueness of the formulation, it turns out that actually you have a global optimal solution, and both the SOCP and the SDP find the same solution. Right? So this is quite unique in that specific setting, but it's an important practical example in the context of communications. So this is interesting because then you can check that indeed your code is correct if you implement using SOCP or SDP. If you have different solution, that means actually your code is incorrect. Right, for this specific example.
Do we mean that SDP can solve a complex problem?
No, but for this specific problem, there is indeed, it is non-convex. When you look at the formulation like this, the original formulation like this, which was original formulation that I showed you, and because at first appearance like this is convex, but the difference of 2 convex functions is not necessarily convex. But this specific problem, even though it doesn't look convex like this, you can formulate this using SOCP, and because of this real part, this quantity there, that you can play on the phase, you can formulate this problem actually really as an SOCP problem, or you can formulate as an SDP problem, and it has been shown that for those specific formulation, there is a unique rank 1 solution that actually is the global optimal solution. But in general, no, this is very specific to that example, right? So if you have a non-convex problem, you will not necessarily find the global optimal solution. But you can have non-convex optimization problem for which you can find global optimal solution. It happens, but in general, it's not the case. Right, so here we have two solutions essentially to solve this, and I think you will see when you play with coursework 3, you're going to play with those SOCP and SDP, so you will become a bit more familiar, you know, with formulating that and writing the CVX code. Right, so let me stop here for 5 minutes, and then we're going to continue with semi-definite relaxation in a bit more details.